Hello everyone. So in the last class, we were starting to build up the process for converting the Navier-Stokes equations into Fourier space. We did it first for the continuity equation. As you can see here, we took a Fourier operator and applied it to the divergence of velocity, which is del xj uj, or del dot u in vector notation, isn't it? And then we used what we had learned about the Fourier transform applied to a derivative. It would be I kappa times the Fourier mode of the velocity itself. So it would be I kappa j uj and or I kappa dot u in Fourier, in vector notation. That would be equal to 0, which means k dot u is equal to 0 according to the continuity equation. So kappa dot u is equal to 0 is your continuity equation in Fourier space. Del xj uj is equal to 0, del j uj is equal to 0, or del dot u is equal to 0 is your continuity equation in physical space. Kappa dot u is equal to 0 is your continuity equation in Fourier space. Now, before we do the Navier-Stokes equations, we wanted to try and set some background for an arbitrary vector, say g hat, and you will see where we are going with this in a few slides. Let's say you have an arbitrary vector g hat, as shown here in this picture, g hat, and which is in an arbitrary direction relative to a wave number vector kappa. And kappa is in 3D space, so kappa 1, kappa 2, kappa 3. I've only shown this as kappa 1 and kappa 2 just for simplification. Let's say you decompose your g hat into g parallel and g perpendicular, which is what you're doing. G parallel to kappa, as in the wave number vector, and perpendicular to the wave number vector kappa. So you have g parallel and g perpendicular. In vector space, that would be g hat is equal to g hat parallel plus g hat perpendicular. Then we expressed g parallel in a different form. So we wrote g parallel as E dot g times E. That is because E is the unit vector in the direction of kappa. So E dot g would give you the magnitude of the wave number vector in the direction of kappa. And then you multiply by E, right? You multiply by E and then you have a vector itself. So if you substitute E for kappa over kappa magnitude, then you'll have kappa dot g divided by kappa squared, which means in index notation that would be gj parallel is kappa j kappa k over kappa squared gk hat. Okay, because what happens here is the dot product becomes kappa k gk, and the kappa outside becomes kappa j, which translates to gj on the left side. Okay, so you have g parallel is kappa j kappa k over kappa squared times g hat. All right. So now, from the fact that g perpendicular is equal to g hat minus g parallel, that is the definition, right? In vector space, g hat, we decompose it into a parallel component and a perpendicular component. So g hat is g parallel plus g perpendicular. So you would have g perpendicular is g minus g parallel. Fine. So g perpendicular is g hat. Instead of g parallel, I substitute this. I have kappa dot g over kappa squared. So essentially, if you use a definition of, say, a new tensor, let's call it pjk. If you use a definition of a tensor pjk, then you can write g perpendicular as pjk times g hat. Now what would be pjk? Pjk would be, in tensor notation, it would be delta jk minus kappa j kappa k over kappa squared. Where did I get that from? Remember, I have g perpendicular in vector notation, isn't it? In vector notations, sorry, in index notation, I'm sorry, is g perpendicular j is g hat j minus kappa j kappa k over kappa squared g hat k. G hat k, isn't it? This is what I have. And so, since I have j, j and k here, I can write this as pjk times g hat, where pjk is delta jk minus kappa j kappa k over kappa squared and multiplied by gk. So this gj became Kronecker delta jk. So I have delta jk minus kappa j kappa k over kappa squared gk. Here what happened is if j is equal to k, then delta becomes 1. If j is not equal to k, then it becomes 0. So that is essentially what will happen here. If you want to find it out for j, if j is equal to k, then all of this becomes j. And that is why you have a 1 for the Kronecker delta. If j is not equal to k, obviously this would become equal to 0. So then you have your g perpendicular is pjk times g hat, or pjk is delta jk minus kappa j kappa k over kappa squared. I hope this is clear. And this tensor is what we call the projection tensor. Because what is it doing? Think about it. You have transformed this vector into the perpendicular vector. You have transformed g hat, an arbitrary vector, into its perpendicular form. So essentially, the projection tensor is determines basically the projection tensor determines g perpendicular to be the projection of g onto a plane that is normal to kappa. Okay, so onto a plane that is perpendicular to kappa. Essentially, it projects g hat onto a plane that is perpendicular to kappa, and that is how you get g perpendicular. So that is what the projection tensor is doing. Now, okay, so let's have the projection tensor set apart. Let's now go directly into the Navier-Stokes equations. This is my Navier-Stokes equations. I have the unsteady term del uj del t. Then I have the nonlinear term del xk of uj uk. You will notice that I wrote it slightly differently. Instead of writing it as uk times del uj del xk, I wrote it as, which is the same as del xk of uj uk. This is because since del uk del xk is equal to 0 according to the continuity equation. So these two turns out to be the same. If you apply the chain rule on the right hand side, you will get two terms. Only one of them will remain. The other term will go to 0 because of the continuity equation. So I will write del xk as uj uk. Now, the reason I am doing this, I'm writing the Navier-Stokes equations in this form, is because I want to take a Fourier transform of a derivative rather than some function multiplied by a derivative. I want to take a Fourier transform of a derivative, and so that is why I wrote it in this form. It's the same, del xk of uj uk. Okay, so that's a nonlinear term. Then you have your viscous term, which is nu del squared uj del xk, and then you have your pressure gradient term, which is minus 1 over rho del p del xj. Now what happens? If you take the Fourier transform of the time derivative, take the Fourier transform of the time derivative. So fk, right? Fk del t uj, del uj del t. And like any derivative, and since it is a time derivative, what you can do is you can switch the Fourier transform and the time derivative. So you can take the time derivative of the Fourier transform because both are independent of each other. So you can take the time derivative of the Fourier mode. That is what this is. So del t of uj. And since the Fourier transform does not depend on, it only depends on wave number. For each wave number, you have a uj. For each wave number, you have a uj, right? For each Fourier mode. So its only independent variable is time because it is discrete. You have a uj hat for each wave number, which only depends on time. That is why this became like a total derivative and not a partial derivative. What you had as a partial derivative, del t of uj, now became d dt of uj hat. Because what you do is you have a uj hat which is a Fourier mode at each wave number kappa. So its only dependency is on time. That is how it became a total derivative. So already you have seen that we are going to be converting a partial differential equation into an ordinary differential equation because we are now writing the time derivative as del t of uj. Obviously, we have to look at the other terms as well, but this is sort of the starting point. Del d dt of uj hat. So that's one term. Now let's take the easy terms first. I will start with the viscous term. The viscous term, if I am taking a Fourier transform of a double derivative, fk of nu del squared uj del xk. So derivative twice, which means I multiply by the I kappa twice. So I will essentially have minus I kappa k and then minus I kappa k. Okay, isn't it? I would have, so here if I take a derivative of fk of del xj g of x, I'll have I kappa j. So there is no negative, I'm sorry. So let me just erase this, start again. So then I would have I kappa k uj I kappa k and then multiplied by I kappa k again because it's a double derivative. I kappa k for first derivative and I kappa k for the second derivative and multiplied by uj hat. So I times I is I squared minus 1 and then I have kappa k which is kappa magnitude squared uj hat. That is what this is. And then I have the nu in there for kinematic viscosity. So the Fourier transform of the viscous term nu del squared uj del xk is just nu kappa squared uj hat. So that's again something very simple. So the time derivative was easy. Fourier transform of the time derivative became equal to an ordinary differential or total differential d dt of uj hat. And the Fourier transform of the diffusion term, of the viscous term, became minus nu kappa squared uj hat. Right? Let's go to the pressure term. If you have the pressure, the Fourier mode of the pressure, p hat of kappa comma t being equal to, and let's just normalize everything, okay? And let's use the dynamic pressure rather than the static pressure, sort of. So instead of taking p, we will take p over rho, just to make matters simple in terms of notations. So we will take a Fourier transform of p over rho rather than just p, because rho is a constant. We are assuming it to be incompressible flow. So rho is just a constant factored in. So your pressure is basically like a normalized pressure p over rho. That's essentially what you're doing. It's like a dynamic pressure. So let's define p hat as a Fourier transform of p over rho. Now the Fourier transform of the pressure gradient term, which is fk of 1 over rho del p del xj. Rho is a constant and that can be factored into p. So you take your p as your normalized pressure p over rho. And then essentially what you have is a derivative of pressure, and you're taking a Fourier transform of that. We now know how to take a Fourier transform for derivative. It just becomes I kappa j p hat, isn't it? I kappa j p hat. Remember, this is a Fourier transform of the negative of the pressure gradient, isn't it? It is basically this term here. It is a Fourier transform of the negative of the pressure gradient, which is minus I kappa j p hat. So that's that. So you just did the time derivative term, the viscous diffusion term, and the pressure gradient term. Notice this is the Fourier transform of the negative of the pressure gradient. So that would be minus I kappa j p hat. Let's take a Fourier transform of the nonlinear term now, the last and final term. And for now, let's write that as a new vector g hat. So g hat in index notation is g hat j kappa comma t. So essentially the Fourier transform of the nonlinear term, we will write that as an arbitrary vector. You will notice I am using the same notation as what I used earlier when I was building up this whole arbitrary vector in the direction of wave number vector and perpendicular to the direction of wave number vector. So you will see the connection soon. But for now, I am going to write the Fourier transform of the nonlinear term as g hat j kappa comma t, which means if I plug in all my manipulations that I've gotten so far, all my derivations I've gotten so far for each term into the Navier-Stokes equations, this is what I have. D dt of uj hat plus nu k squared, because the minus nu kappa squared came onto the left hand side and became nu kappa squared. The pressure gradient term is this one here, because it had a negative pressure, it had a negative value, right? Minus 1 over rho del p del xj. So that became minus I kappa j p hat minus gj hat. This is the nonlinear term. So this is the convection. This is obviously the pressure gradient. This is the viscous term. And this is the time dependent term. As you can see, it is an ODE because you don't have any derivatives except the one that you see on the leftmost side, which is also a total derivative. So your partial derivative has been converted to an ODE, a partial differential equation has been converted to a set of ODEs. And you have d dt of uj hat, isn't it? Which is plus nu k squared uj hat is equal to minus I kappa j p hat minus gj. All of these terms here, the nu k squared uj hat, which is again analytical, it is just product, algebraic product, minus I kappa j p hat, again algebraic product. Then the only thing is gj hat. We still haven't figured out what exactly that is, and that is what we are going to do. But what I want you to appreciate here is we have converted a partial differential equation into an ODE, and that is evident from the d dt of uj, right? So if I take the divergence of the Navier-Stokes equations, and I did this, right? In physical space, I was doing this a lot. When I take the divergence of the Navier-Stokes equations, a lot of the terms go away. The time-dependent term goes away. The viscous term goes away, isn't it? Because del j uj is equal to 0, or del k uk is equal to 0, dummy index. So here I'm doing the same thing. Instead of taking a divergence, since it is in a Fourier space, I multiply by I kappa j, because that's what a divergence does. Del dot u in physical space is del j uj equal to 0, isn't it? Which is in Fourier space, it is I kappa j uj hat, of course. So I kappa j, the multiplication of I kappa j basically takes the divergence, and that's essentially what I'll do. So onto this equation, I will take an I kappa j. So what I'm doing is, you will realize I have d uj dt plus nu kappa squared uj is equal to minus I kappa j p hat plus gj hat. This is obviously hat here. And what I do is, I would just multiply by I kappa j. And what would I have? I would have d dt, sorry, this is d dt, I kappa j uj plus nu k squared I kappa j uj hat. This is uj hat equals I kappa j times minus I kappa j times p hat plus I kappa j gj hat. Now this is equal to 0. This is equal to 0 according to continuity. You only have these terms. I have a I times minus I, which is minus I squared, which is plus 1, and kappa j times kappa j is kappa squared, kappa magnitude squared. It's basically the Laplacian of pressure, which is what kappa squared is. We knew this from physical space. You would get a Laplacian of pressure is equal to the derivative of the nonlinear term. That's essentially what you're getting. You are getting kappa squared p hat, which is Laplacian of pressure, is I kappa j g hat, which is the derivative of the nonlinear term. That is what you're getting. So kappa squared p hat is I kappa j gj hat, which is what I have. And like I said, the above equation, this equation here, is in wave number space the Fourier transform of the Poisson's equation. Because this is the Poisson's equation, right? Del squared p, as in minus del squared p, is del xj of del xk uj uk. This is the nonlinear term, the derivative of that. The Fourier transform of it would be equal to, this is the Laplacian of pressure and the Fourier transform of it. Isn't it? So if you take a Fourier transform of your Poisson's equation, you should get this. Kappa squared p hat is I kappa j gj hat. Now, if you solve for pressure from here, then your p hat is I kappa j gj hat divided by kappa squared. I kappa j gj hat divided by kappa squared. And then if I want to consider the pressure gradient term, it is minus I kappa j p hat, isn't it? It is minus I kappa j p hat here. It is minus I kappa j p hat. I'm sorry, I went too far. It is here. This is the pressure gradient term, minus I kappa j p hat. This is the pressure gradient term. So here what I would have is, going back, minus I kappa j p hat is the pressure gradient term. So I have minus I kappa j p hat would be this multiplied by minus I kappa j. This multiplied by minus I kappa j. So I have kappa j, kappa k, g hat k. What did I do? I have I kappa j, right, or minus I kappa j actually, times, then I have a I kappa j, and then I would, instead of writing this as, remember, kappa j gj in here is a dummy index. I have a j as a dummy index. So I could just switch the indices and write it as kappa k gk divided by kappa squared, which is what this here I'm doing. So I have kappa k gk, then I have the kappa j from this kappa j, and I have kappa k gk over kappa squared. This turns out to be the parallel component, which is gj hat parallel. So essentially the pressure term is balancing minus g parallel. The pressure term is balancing minus G parallel, as in the component of minus G hat in the direction of kappa, right? The pressure term, because I wrote this as minus the pressure gradient, which is what the Navier-Stokes equations had. But the pressure gradient term is basically del P del X. So that del P del X is balancing minus G in the direction of kappa because it is a parallel direction. So what we have done here is we have now taken the time derivative term and the viscous diffusion term and the pressure gradient term. The time derivative term was easy. We just took a Fourier transform of the time derivative term. We got a total derivative of the total time derivative of the Fourier mode of uj. Viscous term was also easy. We had to take a Fourier transform of a double derivative. So it became nu kappa squared. Nu kappa squared times the Fourier mode. And then the pressure gradient term was also relatively easy because we used the Poisson's equation to easily come up with an expression for P hat, which you could not do in physical space, by the way. So P hat is I kappa j gj over kappa squared. And then you write the pressure gradient as minus I kappa j P hat is kappa j kappa k over kappa squared gk. Remember, this became the dummy index. That's why you could just switch from j to k as you went from here to here. So you wrote it as kappa k gk, and then the kappa j is coming from this kappa j. So divided by kappa j. Now this turns out to be the parallel component of G. The parallel component of G. That is what the pressure gradient turns out to be. So that's what we mean by the pressure gradient term exactly balances minus G parallel and the component of minus G in the direction of kappa. In the next class, we will put this all into the Navier-Stokes equations and see what we get. That's it for this class. Thank you.